So this is a video review of the gases of the atmosphere component of GCSE Chemistry and also GCSE Coordinated Science Chemistry. Going to go through all of the different key parts of it. I'm going to recommend you have a think about the answers or maybe jot the answers down before you listen to the answers in the remainder of the video. And that's going to allow you to know where your strengths are and what you need to develop. So let's get straight on. 13.1. Objectives, theory of how our atmosphere developed, interpret evidence and evaluate different theories about the Earth's early atmosphere and when given appropriate information. Data analysis is a big part of this topic. I want you to have a think about the question at the bottom, pause, and when you're ready, press play again. Now, what I'm hoping you've taken from this is that there was nobody there. This was 4.6 billion years ago. We can base it on what we can find in rocks that have existed since then, but we cannot find evidence of anybody or anything that was there that can tell us definitively. So it's very much a theory. We're going to look at the main theory that you will be expected to remember and recall and take elements of. So once again, have a think about these questions, pause and move on when you're ready. Now, it tells us carbon dioxide, water vapour and nitrogen gas. There's actually ammonia in huge amounts as well. So I am going to add that one on, because it is important to know that ammonia was there as a key component. But we want to know what the compounds are. Now, and we need to know the formula of them. Now, as I go through that list, carbon dioxide is CO2, hopefully one you're very familiar with, and water vapour is H2O. Another one I hope you're familiar with. Some of you may have been tempted to write down nitrogen gas, but read the question carefully. That's a molecular element, a diatomic element. It is definitely not a compound. And I mentioned ammonia, and we're going to talk about the formula of ammonia in a moment's time. But what changing condition would have led to the formation of the oceans? We had water vapour in the atmosphere. Well, it makes sense that if the atmosphere cools, the water vapour condenses. It then falls as rain, landing on the Earth's crust, and it sits there as the seas and the oceans. And a little equation there, just so we can see what's happening. The H2O gaseous is becoming H2O liquid. Continuing with theory 1, have a go at the questions, pause. And when you're ready, continue. So I mentioned ammonia earlier, and it's also talking here about methane. Now, methane is CH4. You will be familiar with methane from your work on organic chemistry and the alkanes. And hopefully you're also familiar enough with ammonia from your revision that it's NH3. We make ammonia in the Haber process. It's a key part of the equilibria topic. In terms of the equation for photosynthesis, you have got to remember that we use CO2 and H2O. And we are making C6H12O6, but we're also making O2. I then need to balance it. I've got 6 carbons in glucose, so I need 6 H2O. I've got 12 hydrogens in glucose, so I need 6 H2O. I've now got 18 oxygens on the left. I've got 6 in glucose, so I need 12 more, so that's 6 of the O2. And how can we use this information to explain how oxygen began to form? Well, oxygen was originally a pollutant because nothing that was growing, the bacterial life and the plant life, they didn't need the oxygen. The oxygen was essentially a poison to them, but they were producing it as a part of their photosynthesis. Continuing with theory 1, have a go at these questions. And I'm not going to spend long at all on the equation for respiration. What I'm hoping you recognise is it is exactly the reverse of the equation for photosynthesis. But where did the food for the animals come from? Because we can see the plants make their own food. You'll also be aware that they then respire. Animals can't photosynthesize. They ate the plants. They took the energy in from those plants. And then finally, As the oxygen increased, I've said that was a poison, but evolution meant that there were changes and that plants could start to use the carbon dioxide that was still in the atmosphere, but animals could start to use the oxygen. Now, the brief summary I'm going to break down here. The liquid rock cooled, the solid crust formed, water vapour condensed leading to the oceans, we had life developed in the form of bacteria, followed by the development of plants. Through photosynthesis, these produced O2. As a result, animals evolved to use that O2. And we've been in that symbiotic relationship between plants and animals ever since. We rely on them to give us our oxygen. They rely on us to give them their CO2. Now we're going to move on and take a look at Theory 2, which you're less likely to be asked about in great detail. This is the sort of thing that might come up where you're provided with information in a 6-marker. But it might be solar debris, it could have been comets that were bringing water and bringing things to the planet. Moving on, and we're going to look at the Earth today specifically. And these percentages you will need to learn. Nitrogen 78%, oxygen 21%, argon 0.9%, carbon dioxide only around 0.04. That's a very low percentage. But actually it's gone up by quite a large amount, hence the impact on global warming that I'll talk about later. So I am going to go through the graph. You can see that I have labelled the axes and I've put significant data on there so I can plot the graph, plotted the graph on, and I think what's significant here is just how low the carbon dioxide and other gases are in comparison to the nitrogen and oxygen which predominate in our atmosphere. So we need to be familiar with that data. I'd like to have a read through this. In a moment, I'm going to put up some questions that I then want you to pause and try to work through and see how you feel about them, and then we'll review them. So here are the questions. And as I go through, I'm going to highlight the key parts of the comprehension writing that will help you to find the answers. So carbon dioxide has decreased over time. And we can see lots of reasons why. You might want to pause so you can read them. Oxygen has increased. One key reason there. Ammonia has decreased, and we've got the information down at the bottom. And methane has also decreased for reasons we see down at the bottom. Now for this next question, I'm hoping you found the key information because it tells you what the reactants and products are, and all that is left to do then is to balance them. The balancing of the equation for the reaction of methane with oxygen comes direct from the organic chemistry topics that you have covered as part of your GCSE. So I've got the balanced equation there for you to check. CH4 plus 2O2 goes to CO2 plus 2H2O. And then the common ways that we can see that carbon was removed from the early atmosphere, going to colour code each one here, and we can see it was used up in photosynthesis, trapped in carbonate rocks, or trapped in fossil fuels, dissolved in the oceans. So we've got our key ideas there, and we need to be familiar with all of them. Why have nitrogen volumes not really changed? Well, that's because nitrogen is actually not very reactive, doesn't do much at all. We're going to learn about one specific reaction of nitrogen later in this topic, and we can talk about how we can use it to make ammonia in a different topic, but generally speaking, it doesn't react much at all. Going to move on to 13.3, which is greenhouse gases. Knowing how the greenhouse effect operates, evaluate the quality of evidence in reports about global climate change, knowing how to describe uncertainties in evidence bases, so again we're looking at analysis, and understanding the importance of peer reviewing and looking at as wide a range of evidence as possible. So, what causes the greenhouse effect? Now I'm going to squeeze quite a lot in here, and it is important you get these facts. Electromagnetic radiation enters the Earth's atmosphere. It comes from the sun, comes into the atmosphere. Most of it is absorbed by the Earth, and that's what keeps the Earth at a fairly life-sustaining temperature. But some infrared radiation is radiated back out. Now, you want most of that to leave the atmosphere, but actually, the more greenhouse gases there are, the more of that is trapped in the greenhouse gases. It's absorbed by the greenhouse gases. And that means that the temperature will rise. Now, what's the impact of that? We're going to look more at this later. There's an atmospheric temperature rise. Sea levels will rise because of the ice caps melting. There'll also be more extreme weather. There might be more droughts. There might be more flooding. And that's going to have an impact on habitats, not only on habitats for different animals, but also on where we can grow crops. Again, we'll look at that in more detail later in this video. Now, if we then think about the question at the top here, I think the key is thinking about what sustains life. And if the temperature were below zero, water would be frozen. That makes it very difficult to sustain life. I've also added the label for the y-axis so you can answer the next question. And this is actually a really common question in chemistry, not limited to global warming. When you're asked to describe the shape of a graph, this would almost certainly be a 2-marker. You'll get 1 mark for saying the percentage of carbon dioxide in the atmosphere increases over time. However, you also, to fully explain it, need to say the rate of increase is increasing over time. We know that because the gradient is getting steeper. Moving on, we've got some more practice here on global warming and use of fossil fuels. So if you have a think about the equations for burning propane and butane, hopefully you remember that propane is 3 carbons, butane is 4 carbons. My easy process, best provides help, meth, eth, prop, but, pent, hex. And then you also need to remember that the general formula of an alkane is CnH2n plus 2. So we get C3H8 and C4H10. We have to remember that oxygen is diatomic, and we recognise that in complete combustion we make CO2 and H2O. Now, in combustion of hydrocarbons, I always follow the rule of Joe. I balance the carbons, which I've done here, then I balance the hydrogens, and finally I balance the oxygens. Now, in terms of sources of methane, I've actually not written anything here because we're going to come back and talk about some of these in more detail later on. But methane can come from animal gaseous emissions. It can also come from the decomposition and breakdown of food waste. So we are going to get methane given out in those ways, and that is also a greenhouse gas, so it is a problem. But we're going to move on and we're going to look at how we can analyse evidence. I want you to look at this graph and see what conclusion you would draw just from this about human impact on global warming. What I'm hoping is that you can see that actually within this, it seems very much that there's part of a natural cycle. We've had significant increases before. So somebody could look at this and say, no, we are not responsible for global warming. And that's the evidence that you would draw given only that. Let's take a look at this graph. Now this graph changes the picture ever so slightly. The natural factors average has been laid out and it's a straight line. We can see that it's going directly across, but actually our global temperature has risen. That tells us that we cannot say that the temperature increase is due solely to natural factors. So we're starting to shift in our evidence now. And let's take a look at this graph. What conclusion can you draw here? And what I'm hoping you can see is that there is a clear correlation between the CO2 concentration and the global temperature, which has followed that almost linear pattern following the bar chart very, very clearly. Now, the CO2 concentrations, where they have built up, have come from industrial usage of fossil fuels and a growing usage of fossil fuels. So being able to analyse data like this, again potentially a 6 marker with 2 or 3 graphs provided, is a real skill that you need to be prepared to use. Let's move on. Why might it be difficult to make predictions about what will happen in the future? Well, actually, there's a number of reasons. There are too many factors, really, for us to be able to control what we think will happen. Population changes. If the population carries on rising, are we going to see that having a significant impact? But also, we can look at acceleration versus deceleration of fossil fuel use. What I mean by that is in the UK, we are cutting our use of fossil fuel. But some countries around the world are not yet in a position to do that and are still using coal, using oil in large volumes. So we don't know how that's going to change in the future. And once again, we can speculate and we can theorise, but we also accept that we don't yet fully know what will happen. What we're fairly clear on is the potential impacts. Now, looking at the learning objectives here, knowing how emissions of carbon dioxide and methane can be reduced is important, knowing why actions to reduce greenhouse emissions may be limited, and knowing how to discuss the global scale, risk, and environmental implications. And I've provided here a map which shows what would happen if sea levels rise by 60 metres, which is potentially going to happen. But let's run through some ideas. There'll be a loss of habitat and a loss of landmass as we lose huge areas of coastal, and not even just coastal, London will disappear as the Thames overflows. Now, that will mean a greater population density, and that means there's less land to grow crops. If there's less land to grow crops, the impact of that will be prices for food will rise. And if prices for food rise, the poorest in society will be living in more poverty. So that's just one route through. You can also talk about the socio-political impact of countries almost disappearing and where does that population move to, which countries take them in. Going to move on. I'm going to take a look at what we mean by global footprint. And in very simple terms, it's the total greenhouse emissions that you can take responsibility for. And then some opportunity for you to think about what you can do. Now, this is a good discussion piece within a lesson. It's not hugely likely to come up as an exam question, but again, could play a part in a 6 marker. You could think about transport. Could you walk more? Could you use more public transport rather than getting lifts? You could look at the energy sources that you use. Could you buy from companies that use renewable energy? You can recycle more because recycling uses less energy than making new. And you could look at your energy usage. That might be turning lights off, turning off technology when you're not using it, etc. In terms of what governments could do, well, they can educate. They can put information out there to encourage you. Or they can enforce. They can bring into law things that you must do. They can encourage you, and there might be bonuses that they can give you, there might be money that could be provided, or they could discourage you with fines. So there are lots of different ways that governments can and will use to encourage you to follow the correct path in terms of the environment. In terms of other options, we've got information about carbon capture and storage. Have a think about these questions. Advantages here, it does prevent the increase of gases in the atmosphere, but the disadvantage, energy costs go up by 10%. That's going to be passed on to the consumer, and the government would be thinking about the risk of what that would do if they enforced it. Let's take a look at another example, reducing methane production. Gaseous emissions from cattle. If we eat less meat, we need less cattle. So a plant-based diet would be better. The advantage, it's easy to adapt and it's cheap. The disadvantage is the impact on farmers, specifically cattle farmers, and also how to achieve buy-in and getting people to give up meat. Now let's continue with more questions on this theme. Why is a plant-based diet more efficient with respect to land use? Well, let's imagine that we've got two fields with crops, and all of those crops go to the shop for you to buy. But if we're rearing animals, we need some of those crops to go to the animals, so the animals can go to the shop. Energy efficiency is not 100%. We don't get all of the energy from the plants after they've gone to the animals. But if all crops went to feeding people, we would get far more energy efficiency from that. But again, as I said, getting people to give up meat might be a big stretch. So what other opportunities are there? Well, there are campaigns for a meat-free Monday or going meat-free 1 day a week. Could be something like that. Finally, a summary of the atmospheric pollutants, the problems they cause, where they come from. And I have put together a mind map. I'm not going to talk about this in great detail. I'm going to recommend you pause when we get to the end of the video so you can take a look at the breakdown. Now, to begin with, I've taken each of the different pollutants and I'm now going to colour code and add the causes, any relevant equations, where they are formed, and the impact of the pollutants. And that takes us to the end of this topic. I'm going to let you pause and have a look, see some of the similarities and some of the differences. You need to be familiar with all of the key ideas on this page at this time. Thank you for listening. Goodbye.